All right, hi there, guys. Welcome to another week of critical thinking. So, we really are concluding, right? We are getting really close to the end of the semester. We've done a lot of great work. Thus far, taught you about critical thinking, taught you about arguments, premises, propositions, claims. I taught you about the way those can be sophisticated, those can be worked out. Then, we started thinking about ways of presenting our arguments. And then we stopped and said, well, let's think about how we talk about these things. Because the language we use is actually really important. So that was established. We moved on and we said, sometimes we might be really bad at doing those things. We called those phenomenon fallacies. That was really the story of critical thinking as a greater skill. Now that you know about critical thinking, you can use it in recognizing the arguments around you, the ways everyone around you is constantly trying to shape your opinion, how to articulate your own. We're going to give you all the chance to think about the way science, morality, politics are informed by the way you believe the things you do, what it is you believe, why you believe it, how you can demonstrate that to people, and also ways you can avoid fallacy using fallacious arguments, all the while being very careful about the language you use and interacting respectfully with people in order so that they might truly understand what you mean and not just get locked on the words you say. That's been the story of this class. That's the direction we're going as we conclude. Title of this module is Scientific Thinking. You might be thinking, oh, well, I'm not getting a degree in science. I'm not going to be a scientist. What utility is there for me to think as a scientist? Clearly, you have to take some sort of science class. So immediately there's some sort of inherent value to just knowing what's happening when you perform science. And a lot of you might not be scientists, but you might be going to fields like nursing. This is the same sort of phenomenon that happens in the world of nursing. But also, I just think this sort of skill of applying what's called the scientific method is actually deeply helpful for forming all kinds of beliefs. I know it's been formative for me. And it's still important that you can understand how, for example, if you're building opinions on things in the world of science, technology, engineering, mathematics, that when information is presented to you, you know where that information comes from, you know how experiments are run, you know what hypotheses are, you know how research is performed, right? For our readings, you looked at the scientific method. Reading video, I guess I should say. Scientific method was developed by philosophers really around the period of the Enlightenment as a tool to discover things about the world. There's sort of like a version of the scientific method. Different thinkers have different ways of spelling out the scientific method. But actually, like the sort of process and way of thinking it carries through, irrelevant to which thinker actually is articulating in the example the method itself. These are sort of the steps: make an observation, ask a question, create a hypothesis, design an experiment, make a prediction, test the prediction, analyze the data. This first part here is super important, right? Scientific thinking starts with an observation about the world. There's some sort of phenomenon, some sort of experience, and you don't know why it's happened. This is different than, for example, when I was giving you these arguments about speed limits at the beginning of the semester. I was trying to tell you to imagine a world where there was this new speed limit, and you were thinking about what's called a modal possibility, which is fancy for a hypothetical of a world with that new speed limit. That's not what we do in science. Scientists don't imagine worlds and run experiments there. They observe the world first and seek some sort of explanation for the world. If you've ever heard the story of Newton sitting under an apple tree and an apple falling on his head, he didn't imagine different types of masses and them working in relation to each other, which is, of course, the theory of gravity. He observed an apple fall to his head and asked himself why it was that the apple fell. So science begins by observing a phenomenon inside of the world. There's some phenomenon that you witness and you want to know why it is it happened. You ask a question. In that Isaac Newton example, the phenomenon is an apple falls to my head. The question is, well, why did that apple fall to my head? This is because science is doing something very specific. We assume that nothing happens unless something causes it to happen. I exist because my mom caused me to exist, because her parents caused her to exist, and that sort of goes on infinitely until the first humans emerge. This marker did not just sort of appear into being. Some craftsperson put together the different pieces or created a manufacturing machine that created the pieces. The sort of brute fact of everything that exists in the world is thought to be able to go back all the way until the Big Bang. And from the moment of the Big Bang, all of these things are sort of happening and they're causing other things to happen. And there's this causal chain. There's this list of things causing one another. And what happens is we observe the world and we know for every observation we make of a phenomenon, there must be something that caused it. So you observe the world, there's this phenomenon, and then you say, why did that phenomenon happen? Apple fall on my head. Why did the apple fall on my head? Moving from observation to asking a question. Why did the apple fall on my head? Well, that's because. And then you create some hypothesis. What's a hypothesis? A hypothesis is a story you tell yourself that explains why something has happened. Here's something interesting about these hypotheses. They always have to reflect causes. We call these causal statements. A hypothesis has to be a type of statement that tells you how one thing caused another. It has to be a causal statement. I have to observe the world. I ask myself why the phenomenon happened, and I have to create a statement that explains how one thing caused the phenomenon to occur. At this point, I'm making a guess. I'm making a hypothesis. I'm creating a story. And that story has to be a cause for which the phenomenon is the effect. Here's another thing about hypotheses. They have to be testable. It really could be the world exists. Well, why does the world exist? Because God, or because it just does. That might be true. But a scientist literally can't do anything with that information. That actually reveals something interesting about what scientific thinking is. It's a question of what and how. Science can tell me what causes other things, or how other things happen. How can it do that? Because I can create stories and I can test my stories. If I can't test my story, if there's no way for me to run an experiment on my story, I can't say what happened or how it happened. Therefore, that kind of question is out of the scope of science. That causal statement can't be tested through the scientific method or using scientific thinking. It is beyond the realm of science. It's just not a question a scientist really wants to answer, but even could. So you observe the world, and there's this phenomenon in the world, and you say, well, why did that phenomenon happen? You know what, I bet this is why. I tell a story about why it happened. My statement has to tell a story that explains how it caused the phenomenon. But also importantly, I have to be able to test my story. I can't just have a story that I can't test. And if that is this kind of story I've created, then it's just not a story of science. It's not a scientific question. Our video, which was made for actual science class, so you design an experiment, you predict the experiment, and then you test the experiment. But really what you just do here is you do the test. And you just test that story. Observe the world, why did that phenomenon happen? An apple fell on my head. Well, why did the apple fall on my head? Because it turns out things of smaller mass are attracted to things of bigger mass. Let me test that. We've ran that test ever since we've come up with that theory, and it's come true so far. It works. It explains every observation we've made thus far. This is what science is, right? There are phenomena in the world, and we ask ourselves why these phenomena happen. And we tell ourselves stories of what caused them to happen. And the kind of stories science can reckon with are the kinds of stories that we can test. And then we test and test and test until we find a story that in every single observation we make successfully explains why the phenomenon happens. We've done this a few times. These are what we call laws. Laws are the things that seem to happen in every possible case. Theories are things which happen in every possible case, but we can't control for information that is lost to time, so to say. For example, the theory of evolution will never be able to fully test because we weren't here when the origin of species emerged. In the same way, we are always here when thermodynamics exists. Therefore, it is a law of thermodynamics. The Big Bang Theory is still a theory because it is a story that explains every observation we've made about the origin of the universe that established we weren't there. And so we can't say with due certainty that that is what actually did occur. Analyzing here is just sort of thinking about your results. What does this mean for the scientific community? Also adding it to the library of all human knowledge, of all scientific knowledge. Neil deGrasse Tyson, who's not really a philosopher, but does a lot of philosophy, frankly, talks about that a lot. These stories we tell ourselves shape how humans continue to create in the world of science. What kind of stories is science telling? The kind of stories we can test. It tells us the stories of what things cause other things. It tells us the story of what. And also tells us the story of how, right? If phenomenon X always causes Y, how does Y get here because of X? You could also ask the question, what makes Y? Well, it's X. Here's an example of a question you can ask. Why does Y make X? That's not a scientific question. Science doesn't tell us why. At least it doesn't tell us in a greater sense why. It tells us what has happened and it tells us how it happened. Most people would say science doesn't tell us why. There are philosophers who disagree with this, but alas, that is sort of the general thinking. One final note here about causal statements that I have to include because it's part of the reading. I'm sure you've all heard of the distinction between correlation and causation. Let's say I have a graph and I have these two data points, blue and pink, and I notice that, and let's say that these are two animals, animal X and animal Y. Immediately I can make an observation here about the inversion of these graphs. Say this is time, and this is the amount of these animals. Animal X shoots up in population, and suddenly animal Y dips. There is a correlation with higher amounts of animal X being associated with lower amounts of animal Y. If that notation doesn't make sense to you, that's fine. As long as you understand that that graph there is saying more animal X means less animal Y for some reason. If I just stopped there, all I would have proved is that these numbers correlate with each other. All I would have done is made an observation about the world. Then I might say, well, why did that phenomenon happen? What caused that phenomenon? How did that phenomenon happen? Well, let's say I think it's because animal X started out-competing animal Y for resources. If I run a test and the test proves there was a competition for resources and animal X won, I can prove causation. Notice though, causation emerges as the result of a experiment of one of my tests and the discovery of a story that explained all my observations. Correlation is an observation. It goes up here. Correlations start the conversation about the process of scientific causations are products, stories explaining durations. I'm using the word stories here. You could say theories, you could say hypotheses. But what makes correlation and causation meaningfully different is that they come at two different points in the process of critical thinking, or you could similarly say they come at different points of the scientific method. Correlation you plug in to science, and to prove causation you have to go through the process of scientific thinking. That's why when people say correlation does not equal causation, it's because when you see something's correlated, all you've done is you've made an observation about the world. Now, if you want to prove there's a meaningful relationship between them, you have to think like a scientist, create a story that we can test, and then prove that that test explains all possible observations.